All right, so let's get started. We'll have homework A due on Tuesday next week. Okay, so that's just one reminder. And for classroom disinfection, I asked Isaiah and Joshua for today. Okay, so let's take a look at what we learned last time. So last time we start with again just the fact that if you have current, you will have induced field, and pretty much the origin of current is you have moving charged particles, right? So then the origin, the real origin for the magnetic field, it's because you have moving charged particles, okay? So for that, you can use this equation to calculate the magnetic field produced by a given charged particle that is moving, okay? So if you have V as the vector, and then cross, this is the directional vector with the head from the point of source to your point of interest. Okay, divide by separation square with mu naught divided by 4 pi. Okay, mu naught is the constant. It's called the permeability of vacuum. It's equal to 4 pi times 10 to the negative 7. Q is the charge. Okay. And since we have a cross product of two vectors, so then for the third vector, the resultant vector, you actually can use a right-hand rule to determine its direction. Okay. So in that case, if you have current carrying wire, so that means the charge is moving in that direction, or the positive charge is moving in that direction, in the direction of the current. So then you can kind of see what's the magnetic field. So this right-hand rule here is called the right-hand rule. I think right-hand rule number 1. So you put your thumb in the direction of the current, and then the 4 fingers will curve around in the direction of the magnetic field. Okay, so if you have a straight wire, then you will expect the magnetic field to be surrounding the wire in that circular pattern, with the strength decreasing away from the distance of the wire as r squared. Okay. Now, if you have a wire that carries current, so many times the wire is not straight. It's probably like you have a curved wire. So then for the magnetic field produced by that wire, you will be doing integration. So take a small part of the wire of DL, and you are going to calculate, you are going to actually find, I think this is just a small part of it. So you will have DI here instead. All right, anyway, so you'll be starting with the equation in the previous slides and then doing the derivative of B equals to mu naught over 4 pi times Q times V cross R. So you'll be having DQ, okay? DQ then is equal to I times DT, all right? Because for I, the current is defined as DQ over DT. So you replace that DQ with that, and then it becomes this guy, okay? All right, and then integrating through the whole wire will give you the overall magnetic field produced by that wire at a particular point of interest there. So today we are going to take a look on application again here, the Biot-Savart's law. We will take a look on a thin straight wire here. So if this wire here carries current I, then what will be the magnetic field at the point P? Okay, away, R, distance R away, P is distance R away from the wire. Okay, what will be the magnetic field at the point P? All right, so the starting point again will be the, so let me write this. I think it's not from the starting point there. You'll be doing the work here. So you got a wire there. There's a point P. Which is R distance away. Okay. Oops. So you're picking a small portion of the wire here. So this is your dx, right? And then from there to there, that's the distance r. This is where x is. Okay. So your dB will be equal to mu naught over 4 pi. Let's go to one slice backward here. Okay, so that's mu naught over 4 pi, and then I dl in this case will be dx cross r hat over r square. Okay. So if you move it up. All right. Okay. So this is where you start with. Okay. You can see. So then for the total, see, I'm going to mute everyone. All right. So total field B will be equal to integration of this guy through the whole wire. Okay. And that's equal to integration through the wire of this part. Okay. So mu naught 4 pi I dx cross r over r square. In this case, it would be capital R, okay, because that's the distance. Or actually, no, it's small r, still small r from here to there. Okay. So dx, your dx will be in this direction. All right, that's your r direction. That's your r hat direction from source to the that point. Okay. So when you have dx cross that guy, okay, then it will actually give you because dx, let me see, will have a magnitude of dx, okay, without the hat, right? So then, and then this is 1. So then it will be equal to mu naught 4 pi I dx, okay, times 1 times sine of theta. That's defined as the theta, okay? So that's what we got from the top there, and then divide by r squared. All right, so that's just the magnitude. Okay. And then integration through the wire. So that's how this is coming from. That's from here. And then for the total magnetic field should be integrated through the wire, integrated through that. And then this guy cross that guy will be magnitude will be dx for this term. And then times r will be 1 because this is the unit vector, okay, for the magnitude. So then it'll be just sine of that, okay. Then I think from there we should have the coming steps on the slide. So we can go back to the slide. So in this case, your small r is equal to the capital R square plus x square and then square root. This is the hypotenuse of this right angle triangle there. And then sine of theta should be the opposite, which is r divided by the hypotenuse, which is the square root of that, okay? So, and then when you're doing integration, so through the wire, that means you go from the negative infinity to positive infinity if this is your origin 0, okay? Because this is a long straight wire, okay? So then your integration becomes this guy here. So this is sine will be replaced by that guy, r square, okay? would be, if you do r squared, you get rid of the square root, but you still have this guy, square root of that guy. So that becomes 3/2 for the power in the denominator. On the top here, this is r, okay? Now, this is your integration. Your integration has x squared for the variable here. So when you integrate them from minus infinity to positive infinity, right, you can do just from 0 to positive infinity with the everything multiplied by 2, right, because it's symmetric. So for the negative x direction, it's from minus infinity to 0, but your variable in the integration is x squared, okay? So let's get rid of the minus infinity, okay? So 2 times of that. So that's why you get the 2 pi here instead of 4 pi, because you multiply everything by 2, okay? So originally you have 4 pi, now it becomes 2 pi, because you multiply everything by 2, and then you just do integration from 0 to positive infinity. Integration of this one will give you the result as this guy, okay? So then you can actually look at this up in the integration table pretty much. I think this is something you can find, okay? Basically, you can see if you do, yeah. Yeah, I think that's something you can look up. So we will not go through here, but so then you will have this as a result. So this is your upper limit, this is your lower limit. You plug in your upper limit there. When you plug in your upper limit, so this will be infinity here, this will be infinity square, okay? Now what you can do is you divide numerator and denominator by x. So then on the top here will be 1 over, so then this becomes 1 plus r over x squared, okay? So for infinity large, if for your x, then this whole thing becomes 1, okay? Because r over infinity will be 0 here, okay? So that basically it becomes 1. So then it gives you this term. When you plug in the lower limit over here, then it becomes 0, right? 0 on the top, and then it will be r at the bottom, so that will be 0. So be this term minus 0, which gives you this result, okay? So, and so that gives you the equation for an infinity long wire, straight wire, okay? The magnetic field produced by it at point P, which is distance r away. So it's mu naught times I divided by 2 pi over r, okay? And if you can memorize this equation, then that's the equation you can apply right away, okay? And in a test, this should be given as well. Okay, so this equation will be given as a fundamental equation. All right, so let's take a look on the example associated with this topic here. It says a long straight horizontal wire carries a left to right current of 20 amps. If the wire is placed in a uniform magnetic field of 4.0 times 10 to the minus 5 Tesla, that is directed vertically downward, what's the resultant magnitude of magnetic field 20 centimeters above the wire and then 20 centimeters below the wire? Okay, so let's scratch the problem and then see what this problem is about, okay? So let's say this is the straight wire that carries current. It's a long wire, so you can treat it as an infinity long wire, okay? So current go in this direction, I equals to 20 amps. And there's a magnetic field already in place, the uniform magnetic field that goes down, vertically downward. Okay, so B field. Which has a strength of 4.0 times 10 to the minus 5 Tesla. Okay. What's the resultant magnitude of the magnetic field 20 centimeters above and then below? Okay. So let's say this is our point of interest over here, P point, with this R equal to 20 centimeter, And then you have a second point of interest also 20 meters away from the wire, but below it. Again, this distance 20. Okay. All right, so you have external field, let me call it B1. Now you have a current carrying wire, which will also produce magnetic field in the region around, okay? So then you can let's call this B2 at this point, all right? And then we'll focus on this one first, and then we'll go to the next one in a little bit later. Now, if you have wire like this, you can use your right hand to determine what will be the direction for the magnetic field it produced, right? So you put your thumb in that direction, and then your four fingers curve like that. So above the wire, then you can see your forefinger points out of the wire. So that means above here, this is the direction for your B field pointing out of the paper. Okay. And below here, if you put your four fingers here, you can see at the below the wire, then it's pointing into the paper. Okay, so that's the direction for this B field there, that's into the paper. Okay. Now it looks like it's going to be a three-dimensional scenario here. So let's pick this as, let's put this as X direction, this as Y direction, and then this as Z direction, okay? So for the magnetic field at this point, then it's going to be due to the already existing external magnetic field plus the magnetic field produced by the current carrying wire, right? So it'll be B1 plus B2. So for the total current A, that would be equal to B1 plus B2, and then magnetic field is vector, so we do a vector addition here. All right. So as we set it up this way, so our B1 will be then 4.0 times 10 to the minus 5 Tesla, and that's in the negative Z direction, so minus K direction. Okay. For this guy here, B2, we can calculate the magnitude by using the equation we have in the previous slide. So mu naught I divided by 2 pi times R, right? So that's magnetic field by a straight wire, long wire. You can calculate what's this B2. So B2 equals to 4 pi times 10 to the minus 7 times I, 20 amps, divided by 2 pi times R, which is 20. This is in centimeters, so you want to convert it into meter. So 0.2 meters. Okay. So you can see this 2 pi then will partially cancel out that 4 pi with 2 remain. Then you can calculate what's the B field here. So it's going to be 2.0 times 10 to the minus 5 Tesla. Okay. On that guy. So that's B2, the magnitude. Now you can see B2 is pointing out of the board here. So then B2 should be in the positive X direction. Okay, so we can plus B2, which is 2.0 times 10 to the minus 5 Tesla times positive I direction. Okay. So then you can see, you know, B field, if you put in the order of X first, and then the K next will be 2.0 times 10 to the minus 5 Tesla in I direction minus 4.0 times 10 to the minus 5 Tesla in K direction. Okay. Now it asks us to find the magnitude, right? So we have the components here, then we can calculate for the magnitude. The magnitude will be the X component square plus the Y component square. Now Y component is negative. So square root of 2.0 times 10 to the minus 5 Tesla square plus minus of 4.0 times 10 to the minus 5 Tesla, okay, squared. So you got your component B magnitude to be 4.47 times 10 to the minus 5 Tesla. Okay. Now on the second part, you'll do the same B1 plus B2, but this time B1, that is B2 here, B1 is still the same. B2 is pointing into the board. Okay, so instead of having positive I for B2, it's going to be having negative I. Okay, so basically that's just the direction change there. So you can write it down quickly. So this should be minus 2.0 times 10 to the minus 5 Tesla in the I direction, minus 4.0 times 10 to the minus 5 Tesla in the K direction. K direction, vertical direction, it doesn't change. Okay, so because you only switch the sign here, so the magnitude would not be changing. Okay, so it'll be the same because you are doing square of it and then take square root, so it'll be still the same magnitude. Okay. All right. Questions you guys might have on this? All right. So if not, we'll move on to next section here on the magnetic force between two parallel currents or current carrying wires. Okay, so if we have two wires in space close to each other, both carrying currents I1 and I2, they are separated by R. Now you can imagine that for one of the wire, if you just look at it first, and then you'll see that it will produce a magnetic field in the circular form, right? Now the second wire then is placed into the magnetic field produced by the first wire. So if you have a current carrying wire, you have a magnetic field, then this guy, the second wire will experience magnetic field, okay, or magnetic force. So magnetic field produced by wire one is equal to this guy, the mu naught I over 2 pi r. Okay, so the equation at the bottom here. Then the force the second current carrying wire experience will be equal to the I of it times L times B. Okay, so that's for current carrying wire, it will experience that much of force. So then for force, if you have two wires close to each other, they will have force on each of them. Okay, so it's the kind of action and reaction force between the two. So force is turned out to be, so if you put these two together, replacing B1 with this guy here, now behind this taskbar here, but with that equation, B1 equation, okay, replace the B1 with this mu naught I1 over 2 pi r, then you pretty much get F equal to mu naught I1 I2 times L divided by 2 pi r. Now, in this equation, you already move L to the other side of the equation, so it's L divided by F, okay? So that means the force per unit length, if you are just looking at the force, then the L goes on the other side, okay? So be mu naught I1 I2 L divided by 2 pi r in that case. If the two wires carries the current in the same direction, now the force between them will be repulsive force, you can see here. So you can use one right-hand rule here to determine the direction of your current. So to be going in in this circular direction, right? So then at this particular point over here, your B1 is in that direction, pointing inside the board. And then this is the current direction. Now you use the right-hand rule here, the second right-hand rule here, where your thumb goes in the direction of the current, and yeah, I would do it this way because it's F is equal to I cross B, so you can put it up this way. So this is I cross B field, then this is the force, okay? So the force then is towards this guy because F is equal to I cross B with the L, okay? So then it goes in that direction. And similarly, if you use your right hand rules, you can also determine on this one, it will experience magnetic force by the magnetic field produced by this wire. So that will be in this direction, okay? If you have the currents carrying opposite current, or the two wires carrying opposite, the direction of current in them are in the opposite direction, then the force between them will be repulsive, okay? So they will be pointing away from each other. All right. So on this one, we'll take a look on this example here. It says two long straight wires are parallel and 10 centimeters apart. One carries a current of 2.0 amps and the other carries a current of 5.0 amps. So if the two currents flow in opposite directions, what's the magnitude and direction of force per unit length of one wire on the other? And then what's the magnitude and direction of the force per unit length if the currents flowing in the same direction? Okay, so I think for the magnitude, in the two scenarios, that would be the same. Okay, so that's I think that's easy to answer. But for the direction wise, if you have two currents, they are in opposite directions, then you will have repulsive force between the two. If you have them in the same direction, you will have attractive force. Okay, so but let's calculate what would be the magnitude. Okay, so you guys can give it a try. I think it's pretty much just plug in the numbers on the equation in the previous slides. You can do that. We can take a look on the solution together in a couple of minutes. Okay. So it will be F over L equals to mu naught I1, I2 divided by 2 pi R. R is the distance between the two. Mu naught is 4 pi times 10 to the minus 7. All right. So I think we can take a look at this one together now. So mu naught is the 4 pi times 10 to the minus 7 Tesla meters over amps. I1, so you'll pick one of them as 2.0, and then the other one should be 5 divided by 2 pi. Now R is in centimeters, so you want to convert it into meters, okay? So the 2 pi and then 4 pi will cancel out partially. So you'll see then this is 2. So 2 times 5 is 10, so 20. Okay, so 20 divided by 0.1 will be 200. 200 then will be 2 times 10 to the minus 5. Okay, that should be in newtons over meters. Okay, so that should be the magnitude. Okay, for the magnetic force. All right. And then for the direction, I think on A you can just say repulsive. Okay, to each other. And then on B, it will be the same magnitude. Okay, so magnitude will be the same. And should be attractive force. Okay, because they are in the currents are in the same direction. So then the force is attractive force. Okay. All right. Let me know if you have any questions on this. Okay. So if not, then we'll move on to the magnetic field by a current loop. So in this case, we'll be looking at the circular loop. Okay. So again, you start with take a small portion from the loop, so then you get the IDL there. Okay. So IDL sine of theta again, it's the direction with R and DL. But in this case, then these two are perpendicular to each other, right? If you take a small portion, then sine theta will actually go away, become 1. Then you integrate through the loop. Okay, so integrate through the loop there. Then the I is the constant, mu naught 4 pi, and then R squared is also constant. Okay, so then you are pretty much just integrate things through the DL, the small portion of the loop, and through the loop itself. So then just integrate in that one. Okay, so if you are integrating through the loop, it will give you the circumference of this circle, 2 pi times R. So 2 pi R and then 4 pi R squared cancel partially. So your result will be 2 times R in the denominator. So mu naught times I over 2R. Okay, that will be what you have at the center of loop. Okay, for the magnetic force or magnetic field. Okay, so this one is a little bit simpler. It doesn't have pi in it. Okay. So you can compare the two. For a straight wire at distance r where you are having mu naught I divided by 2 pi r. For a loop at the center of loop, you only have mu naught I divided by 2r. Okay. And we can take a quick look on this example here together. It says when the current through a circular loop is 6 amps, the magnetic field at its center is 2.0 times 10 to the minus 4. What's the radius of loop? Okay, so you apply this equation, the B equal to mu naught I times divided by 2r, and then you solve for r in this case. B field is equal to mu naught I over 4R. And then R then will be equal to okay. So then 4 pi times 10 to the minus 7 times the current divided by 2 times 2.0 times 10 to the minus 4 Tesla. That will be equal to 0.019 meters. Okay. Not done yet. All right. So we took a look on the for the B field at the center of the loop. Now, what if you are looking for the B field that is on the axis that going through the center perpendicular to the loop, but a distance in this case should be z away. Okay, so from here to here is distance z away. What will be the B field over here? Okay, so this is something similar to when we determine what will be an electric field. Okay, by charge distribution. Okay, so you can take a small portion of this guy and then determine what will be the B field, the direction of it here. So you can find a counterpart on the other side over here. So then it will be in the opposite direction. Okay, so you can see the y component B field will cancel out. So the resultant will be you only have B field in the z direction, in this direction. Okay, because this is pointing this way. If you pick another portion here, it will be pointing in the other way around. So then the vertical direction component will cancel out. You only have this kind of horizontal component. Okay. All right, so then we'll be just focusing on the z component for the B field. Okay, so z component then will be equal to the mu naught I dl. Okay, because that's what we have in the previous slides. Now we have a sine theta here because now this is the angle theta. Okay, so this is angle theta. Sine theta will give you the component for this guy. Okay, so if this is angle theta, this will be theta, this will be theta. So you are taking this component of it, okay? So sine theta gives you the z component of this dB, right? And then over r squared. Now you'll integrate through the ring, okay, of it. So in this case, because you are z away from here, so theta is also a constant. So sine theta and I mu naught, they are all before the integration. 4 pi r squared, r is this small r. It should be also the fixed length if you go through the circle, okay? So again, you are integrating through this with the only variable being the L, okay? There's no L there, so that means you will be doing the using the circumference of it because you are integrating through the whole ring. Okay, so 2 pi r there. All right. Then again, 2 pi and then 4 pi will cancel out partially. You have 2 remains. So mu naught I divided by 2. Okay. And now the sine theta is this theta here. So R, capital R over this. Okay. This small r, the longer r, small r. Small r is square root of r squared plus z squared. So sine theta is r divided by square root of it. Okay. and then small r here, you still have that r squared. Okay, so then you have this guy in addition of the sine theta here, r here. So then it's this guy to the third power in the denominator, which is this guy of 3/2. Okay, the square root to the third power is the 3/2 of this. On the top here, you originally have a capital R. You get another capital R from sine theta. So you have capital R square on the top. Okay. So then your B field will be just in the Z direction with this magnitude, which actually also should apply for the B field at the center. In that case, then you simply replace Z with 0, right? So that means you are at the center, which is 0. Then it will give you mu naught I divided by capital 2 times capital R, because this is R squared. At the bottom here, you will have R to the Q, okay, in that sense. All right. Any questions you guys might have on this one before I move on? Okay. So if not, then you can see actually for the magnetic field produced by a current loop. Okay, so we can use right hand rule. At any point, we can use our right hand to point in the direction of the current, and then forefinger will curl around along the direction of the magnetic field. So you have magnetic field then in this fashion, right? For the magnetic field produced by a current loop. And that's similar to if you have a bar magnet of having south pole here, north pole here, right? So that's the same magnetic field you would expect from this, okay? So in that case, you can model or like replace the magnetic field produced by a current loop with a bar magnetic, okay? So in that sense, so depends on what's the current of your direction of your current. Now, if you have two, they are placed together, two loops placed together, so you can see it will be attractive force, okay? And then if you have the current in the opposite direction, you have two loops that carry in opposite direction of current, then they will repel each other, okay, in that sense. Just like a bar magnetic would do, okay? All right. Next section here talks about Ampere's law, which is very similar to Gauss's law, where Gauss's law says the electric field produced by charge field by charge should be equal to the flux, electric flux should be equal to the charge enclosed divided by epsilon naught. In here, it's similar here, but we'll be taking a closed path instead of a closed surface. Okay, so if you have currents, and then if you have a closed path, so then the integration of the B field times the dl from the path, the small dl from the path, that should be equal to mu naught times I enclosed. Okay, or if you're doing summation, then you divide the loop into small pieces. Okay, so in that case, it will be the same. So you replace integration with summation in there. All right. And this mu naught again is the constant, and then it's called the it's called the permeability of free space, not permittivity. Permittivity again is referred to epsilon naught. Okay, so this is mu naught. Let me just see if I can change it now. Okay. All right. So let's take a look on how you apply Ampere's law here in this case quickly. So if you have a closed loop, you can draw a closed loop that is r distance away from the wire, current carrying wire. So then when you're doing integration of B field through this guy, so it will be B times 2 pi r, right? Equals to mu naught over mu naught times I. Let me show it here on the paper. So in this case, when you apply Ampere's law, you'll write integration through the closed path dl equals to mu naught times I. Okay. Now, if you are equal distance away from the current, B field is a constant. So B times integration through dl, right? Through the loop mu naught I, and then this will be giving you 2 pi times r. So then B times 2 pi times r equals to mu naught times I. That tells you B is equal to mu naught I over 2 pi r. Okay. So that's how apply Ampere's law here. And it gives you the result pretty handy with this guy, right? So this is the same as what we got about maybe 3 slides back. Over, yeah, quite a few slides back over here. Okay, so if you have a current carrying wire, you can do it this way. So there's a couple of ways you can do it. You can do integration through to get this, or you can apply what we just learned, the Ampere's law here to this guy, then you get the result directly. Okay, just apply Ampere's law, integration through the closed path, B times dl equals to mu naught times I, and a couple of steps. Okay, much easier to apply Ampere's law here. Similar to Gauss's law, when you apply Gauss's law to find electric field, it's much easier. Okay, in some cases. All right. Let's take a look on this example here. It says a hypothetical current flowing in the z direction creates the field B equals to C times x over y squared for the I component plus 1 over y for the j component in the rectangular region of the xy plane showing in the accompanying figure. Use Ampere's law to find the current through the rectangle. So it wants us to use Ampere's law. So that means you want to use integration of B field. Okay. So we will then use this rectangular shape rectangle as our enclosed path. So going from one side and then the second side, third side, fourth side there. Okay. So let me see. I think I'm going to start with this point over here and go back to that point. Okay. So and it has B field. So B field written as B is equal to C is a constant, a given constant number X over Y squared times I direction plus 1 over Y, the J direction. Okay, so this is my C field, my B field. So then I have to go through the 4 passes here. Okay, so B times DL, that means I'm going to take a small DL on this path going in that way. Okay, so then in this case, DL is in the direction of J, right? And then you are doing dot product. So that means you only have J dot J because I dot J will be 0, J dot J will be 1. Okay, so then you'll be doing, let's do it this way. So integration from B1 to B2 of my B field dot my DL, okay, that would be my dy, right? My dy direction. And plus the next one, I will go from A1 to A2. So integration of A1 to A2, the B field, the DL in this case would be in this X direction. Okay, so the X direction. And then plus the third part here, this would be again in the dy direction, negative Y direction. Okay. But I don't care. I will go from B2 to B1. Okay, so I go from B2 to B1. My B field, my dy direction, and then plus the last piece here will be from, now I go from A2 to A1. My B field that's in the Y direction. All right. So the first part here, I'll use this dot dy or the J direction. So then that means I only have this guy, right? So I have, but I still have C here. So C over Y on that one. Going from B1 to B2 and then integration of dy. On the second one here, from here to here, I go from A1 to A2. I will only have this one, right? Remains. So my CX over my Y square. So in this case, my Y from here to here, my Y is fixed, right? My Y is B2. So my B2 square. Right? And then this is dx plus the third one from B2 to B1. And my B field against this guy dot dy. So again, I will take the second one. Okay, the second term there. So this is again C over Y dy plus the last one from A2 to A1. B field dot dy. I think a d dot dx. Sorry. So the last one should be dot dx. Again, then I only have the first one dot dx. Okay, so then x over y2 or y square. Sorry, y square. In this case, you go from here to here. Your y doesn't change. Your y is b1, so b1 square dx. Okay. So Ampere's law says if you integrate through that, that should give you the mu naught times the I, right? So if I can calculate this guy, then my I will be whatever I calculate from this side divided by mu naught. Okay, so that's what we are doing for right now, just calculating from for the left-hand side equation. Okay. So you're going from here to here. So this will give you, actually, I think we can just take a look on this guy and this guy, right? They are exactly the same integrations, but you go from B1 to B2, here you go from B2 to B1. So they will actually cancel out, right? Because one will be positive, one will be negative, okay? If you do that. But anyway, if you are integrating that, it will be C times line of Y, right? Because this is C over Y And then going from B1 to B2 for the first one. And then on the second one, this is X. So it become X squared and then 1/2. So you have C B2 squared times 1/2 X squared, right? A1, A2. And this guy will be C ln Y from B2 to B1. And then at this point, you should be able to see this one and this one will cancel out here because they are opposite, having opposite limits. And then plus the last one here would be, am I missing a C factor here? Yes, I think I am because there's C in front, so C there. So C over B1 square, now 1/2 X square from A2 to A1, okay. This term and this term will not cancel out because B1 and B2, they are different, okay? So we only have one cancellation. The other one will not cancel out. That would be C over B2 square 1/2 of A2 square minus A1 square, okay? On this guy, plus C over B1 square times 1/2 of A1 square minus A2 square. Okay, so you can make this as like negative. So negative of this one and then negative of this one, right? You can put the two negatives there. So then this is the same as that one. So then you'll have C over B2 square minus C over B1 square. And then there's 1/2 times A2 square minus A1 square. Okay, and all this will be equal to, so this is your left-hand side equation here will be equal to your right-hand side equation there. So then divided by mu naught will be equal to, you can put mu naught here, 2 times mu naught, okay, or mu naught times 2. That will be your final result there. That will be your current, okay, going through that rectangular area. All right. Okay. All right, so I think we will stop here for today then.